All right, let's go ahead and get started. Sorry about that. My computer bombed right when I had to reboot the whole thing. So again, once again, sorry for being out last week. I was at a NASA meeting all week. I would have rather been here, but it was still interesting. I trust that Mark did a good job on Tuesday, and though he said you guys didn't ask a lot of questions, and I've noticed the same thing, and I really want to encourage you to ask questions during the lecture. So I don't bite. I don't think Mark does either. So ask questions if you have them. So I also assume that, at least I heard from Margaret, that the STK lab went fine. That was a very simple lab. It's just really supposed to design to just get you some familiarity with STK. So if you'd used STK before, it was probably completely boring, but hopefully you kind of learned the lay of the land, and the labs will get kind of more difficult as we go through. So I don't think the next one is still a few weeks off. So today I'm going to talk a little bit more about orbital elements, because it's a pretty important topic. I know Mark introduced those concepts Tuesday, and I talked about it a little bit before that. Before we get into the lecture, though, just want to do my usual space news updates. The one I saw yesterday, this was interesting just because, not so much the news, but because I liked the plot. So because it was talking about the Blue Origin's new booster, new rocket, and comparing them in size to all the other rockets. So including the Saturn V, which is probably the most interesting, because the Saturn V was one big rocket, and so Blue Origin is now proposing this new this Glenn booster, which is not quite as big as the Saturn V, but it's getting there. Probably more important to Blue Origin is that they have a bigger rocket now than Falcon 9 at SpaceX. So but anyways, it'll be interesting to see how these ventures move forward. Kind of related to that, last week, the OSIRIS-REx launched successfully, but Amos 6 did not. So you've probably all seen these, but let me, so here is the launch of OSIRIS-REx. 3, 2, 1. And liftoff of OSIRIS-REx. This satellite's going to the asteroid Bennu, and our own doctors and professors Dan Shears and Jay McMahon are actually involved in this mission. Dr. Shears is I think he's the principal investigator for the radio science team, which means he's not head of the mission, but he's head of the part which is going to determine the gravity field and shape of the asteroid. So it'll take 2 years to get there, so they have a while to wait before they can do other things. But let's see here.
28.
And then, but then there was
Go Atlas.
Working the satellite business.
Go OSIRIS-REx.
Everyone is go.
Let's get rid of that one. And then there are ones that aren't so successful. So, and this was so spectacular.
A SpaceX rocket exploded on its launch pad this morning at the Cape Canaveral Air Force Station. No one was injured, but the unmanned Falcon rocket.
I don't need to listen to her. Let's see here. Oh, I had a better video than
SpaceX was
that.
working to conduct engine test flight.
That's the problem when your computer dies right before you walk into class. So,
there are times when we make history.
no, we did not make history today. Okay. There you go. That's the short version. I want the long version. What's going on here? This is so good. We got to replay this. So what's interesting here is that if you watch it long enough, you'll see the rocket, or the satellite, and the cone of the rocket falling off right there. So you know you've had a bad day. almost everybody that watched this immediately, you don't have to be a rocket scientist to realize that it was the second stage that exploded. It wasn't the part that's going to launch the whole thing. It's what's going to propel the satellite into its orbit after you get into Earth orbit. So something went wrong with the second stage. So, oh yeah. Yeah, there it is. Oh, maybe this one's got a better. And also, this was not the launch. This was. I wonder if somebody photoshopped that in. So. I actually saw a quote, though, from Elon Musk that said he had not ruled out that some foreign object had hit the vehicle. So, but this is the first time it happened in what they call static tests. So, right. Rockets blow up all the time. I mean, if you. Oh yeah. So. Anyways, that's enough of that kind of stuff. But
I read that Elon Musk is asking for all the video from the public that took video because there's a.
Yeah, what is that thing there?
He said that there was a bang before it exploded. So I don't. So they're trying to figure out what the bang.
Actually, this is actually from the new version of the X-Files they're filming. So. Okay. But actually, I have not seen an explosion quite that spectacular. So let's go on to the lecture, which unfortunately, how could my lecture be as exciting as that rocket blowing up? Especially when I'm going to talk about Kepler's equation. But I did get some questions in office hours and stuff about Kepler's equation. And so I had a few other slides that I hadn't shown that I wanted to just go through and make sure everybody understands why we're using Newton-Raphson technique to solve Kepler's equation and things like that. So and then we'll get back to talking about orbit elements and what else is on the agenda today, F and G series. And at the end, we'll start talking a little bit about reference frames kind of in preparation for the next lecture, which Thursday I'll start getting into reference frames. So in fact, Mark, I had a debrief from Mark after I got back, and he said they didn't know what sidereal was. And I said, well, that's because I don't introduce sidereal until I talk about time systems and reference. So I guess sidereal came up in the context of how you define a geosynchronous orbit. And the way that's going to come up is that it will, a geosynchronous orbit is one that matches the rotation of the Earth. So the orbital period is exactly the rotation of the Earth. But what we're going to learn is that there's different ways to measure the rotation of the Earth. Does the Earth rotate once around with respect to the sun, which is 24 hours? That's how we define a day. Or does it rotate once around with respect to the stars? And that's 23 hours and 56 minutes and some seconds. And so they're different. And so that's the sidereal rotation rate, the rotation with respect to the stars. And that's actually the one you use to define a geosynchronous orbit. So, but I always introduce that stuff in the next couple lectures. So we'll start getting into that on Thursday and finish off some of the orbit element discussion here. So, so this, of course, is the famous Kepler's equation. And, we use this in a couple of different ways. We use it both when we're transforming from position and velocity to orbit elements and from orbit elements back to position and velocity. And so if you have a set of orbit elements, then you can compute the eccentric anomaly and stick it in here and get the mean anomaly and then solve for time by knowing the mean motion. Because remember, the mean anomaly is the mean motion times time past periapse. But if you have the mean anomaly, and you're trying to solve the eccentric anomaly, then this is a nonlinear equation. And you have to be able to solve that nonlinear equation. So this Newton-Raphson technique is not special to Kepler's equation. You can use it to solve lots of different nonlinear equations as long as they're not two wildly behaved functions, as I'll show you here in a minute. If you took a class in numerical methods, or maybe some of you have had a class in numerical methods, you probably would have encountered this Newton-Raphson technique there. So we're going to solve this, and we want to know how m varies as a function of e and vice versa. So for a circular orbit or an eccentric orbit, we get different relationships between the mean anomaly and the eccentric anomaly. So on the left here, we have a near circular orbit. The eccentricity is 0.1. Of course, we know for a circular orbit, the mean anomaly is equal to the eccentric anomaly. So that would, for a circular orbit, this would just be a straight line. So for an orbit that's close to circular, we expect something close to a straight line, but you can see it's not maybe you can't see, but it's not a perfect straight line here. But the closer we get to eccentricity of 0, the more this becomes a straight line, and then it's trivial to solve these because it's just m equal to e. So for an eccentricity of 0.5, though, you start to get quite a bit of curvature in here. And then if you go all the way out to eccentricity of 0.99, which is, in my mind, is getting into the range where you probably don't want to use Newton-Raphson's technique anymore, because it takes longer to converge out here, as I'll show you on the plots a little later. The other thing that we're going to talk about is this will be illustrated in the slides, but remember the Newton-Raphson technique is using the slope of the function to predict what the next guess should be. But you can see it's most obvious if you look here at this plot, the slope is changing throughout here. And so there's a lot of curvature here, a lot of curvature here, and so you might expect that the number of iterations that you have to go through Newton-Raphson's with might be different depending on whether you're trying to solve for an eccentric anomaly down here or, say, in here. So, because all we have is the slope. We're not using, remember, we derived this Newton-Raphson technique by doing a Taylor series expansion about some initial guess, but we ignored all the higher order terms. So the Newton-Raphson technique only knows about the slope, it doesn't know about the curvature, because we ignored those higher order terms. So in an area where the slope is a good representation of the function, then it's going to converge rather quickly, the Newton-Raphson technique. But in an area where there's a lot of curvature, then the slope isn't going to be a good representative of that, and it's going to take more iterations to get this to converge. So let's say we have an eccentricity of 0.1 and a mean anomaly of 100 degrees. And so we want to know what is the eccentricity that corresponds to a mean anomaly of 100 degrees. So one way to do that is to, first of all, move m over to the other side of the equation and call that m target. So, or it could be m initial or whatever you care to call it. But this would be our mean anomaly. So we're going to say that's 100 degrees. And then we're going to plot out this function. And so we compute everything here. If we use an initial value of the eccentric anomaly that corresponds to the mean anomaly, then we can use that as our first iteration. So so we start by moving the mean anomaly to this side of the equation. So we subtract off the mean anomaly from here. If we subtract off 100, we get this plot. And so now we want to know what is the value of E that makes this thing 0, which is going to be this 0 here. So, and now we're dealing with E of 100, but the blue line here is looking at what would have to be plotted out, all the possible E's you might be going after. But we're looking at what happens when we want to find E corresponding to M of 100. So we start with our initial guess. And so we're going to guess the E0 guess. We're going to start with the mean anomaly. Of course, that's a really good guess when the eccentricities are small. It's not as good when the eccentricities are bigger. So if you stick in E0 here equal to M, then you compute this equation. If you have the right E, you're going to get 0. If you don't have the right E, then it won't be 0. Yes?
When we're doing for the eccentric anomaly, do we have to keep it in radians? Like when we're doing?
Yes. Yes. When you're solving this equation, everything should be in radians. So It's easier to visualize when you talk about degrees because it's easy to visualize for most of us 100 degrees rather than 1.745 radians, but when you code it, you need to code it in radians. So so you compute this equation and you don't get 0, you get minus 5.64 degrees. For this particular iteration, so E is m, so these terms cancel, and this E sine E thing here ends up being minus 5.64 degrees. So that's not the right answer. We wanted to find E that drives us to 0. We didn't get that, and so now we need to figure out how to get there. So we want to modify the guess, and we want to find what drives us to 0. So I've blown up this part of the chart here. Here's where we ended up. We ended up at minus 5.64 degrees. We want to be at 0. And so the way we predict the next initial guess is by using the slope. So we compute the derivative of the function, of that function. So we compute the derivative right here, evaluated at m equal, actually in this case, for this iteration, it'll be the E0. So it'll be 100. And so we evaluate the derivative. We use the derivative to predict what's going to drive that function to 0. So we're using the slope to predict where the 0 crossing is. So if this is linear, then that's going to do a really good job and it will converge in one iteration. If this has some curvature to it, then the slope is not going to predict it exactly, and so we're going to have to do another iteration. So that's what we do here. Use the slope. We predict the next point, the next guess. We put the guess in. We compute the value and see if this is 0. If it's not 0, then we have to do another iteration. And that's basically what the Newton-Raphson method is applied to Kepler's equation. So this is from previously in the notes, but we're trying to solve this equation. We're finding E that drives it to 0. We also use the slope of that equation, that function, f prime of E. So the slope here is minus E plus E cosine E. And the way we implement that is through these guesses. So you have your nth guess, and you're basically computing a correction to that to get your next guess. And the way you can check if this converges is by comparing the previous guess to the new guess. And when the differences start getting small, then to whatever tolerance you desire, you can set the tolerance to be like 0.00001 or whatever you want. Then you're done. So going back to our example here with eccentricity of 0.1 and mean anomaly of 100 degrees. So we're starting with our initial guess of E0 equal to 100, which was just the mean anomaly. The value of that function ended up being minus 5.64 degrees. So then we use the slope computed here, and we use that to guess where the 0 crossing is. So we're using this answer plus the slope, and we get that the next guess is E1 as 105.546 degrees. We recompute the value of our function there, and it's 0.0263. And we go on, third guess there, we're actually to within the digits, 4 digits there, we're at 0. And so we can stop. And so when you start comparing, if you just keep on comparing, you start up with comparing E1 to E0, E2 to E1, E3 to E2. When these two are going to be less than 0.0000, so that would be saying it's converged. So it's pretty straightforward. So for eccentricity 0.1, are there any challenges? No, it's straightforward. It'll probably converge in a couple of iterations. But an eccentricity of 0.95, it's going to take more iterations to converge, as I'll show you, but it's really not a challenge in terms of getting that to converge. But let's look at that eccentricity of 0.95. So let's say your mean anomaly is 180 degrees, and you're trying to solve for the eccentric anomaly that corresponds to that mean anomaly of 180 degrees. So we start doing the calculation. So your first guess is just the mean anomaly, again, 180 degrees. But you see the error is already 0, even after. So the first guess is actually the right one. And that's because we also know that the eccentric anomaly and the mean anomaly agree at periaps and at apoaps. So this is at apoaps, and so the first guess is the right guess, and it converges. But also note that this whole region here is fairly linear, so even close to 180 in that region, we should be able to converge in one or two guesses, iterations. But what if we're up at this end where there's a lot of curvature? So there's a lot of curvature. We start, let's say we're starting with 300 degrees. The first value we get out is actually 47 degrees. And you can see the next iteration, it's even bigger difference. And then finally it does converge in. Takes a while to get there, but it converges down, and we finally get down to about the 0.0000 level on iteration 5. And that's taking longer because of the curvature here. Remember, you could develop a more sophisticated technique that used the higher order derivatives of the function. Because remember, this was a Taylor series expansion. So we had f prime, f double prime, f triple prime, but we ignored the higher order terms. And the reason you do that is because you just don't want to go, it's tedious to go and compute all those other derivatives and develop a higher order predictor. So if you know it's going to converge, why not just use a single value of the derivative, the f prime, and iterate it and let it converge. So what if we have 350 degrees, still an eccentricity of 0.95? Well, you can see there, it's also similarly starts out 9 degrees, but then goes out, there's an error of 125 degrees, 25, 5, and then finally it converges down. But it takes 6 iterations. So we can look at the number of iterations. How many iterations does it take for an eccentricity of 0? Well, obviously that's just 1 because they're equal, so you don't have to iterate it. What about if you have an eccentricity of 0.5? So you can see for 0.5, when you're at periaps or at apoaps, it only takes 1 iteration because they're equal when you're exactly at periaps or apoaps. But the farther away you get from periaps or apoaps, the more curvature you have in that function. And so the more iterations it's going to take to converge, up to 5 iterations for an eccentricity of 0.5. What about an eccentricity of 0.9? It can take up to 7 iterations. So, but you can see the number of iterations here. It does vary with where you are in the orbit. And so if you're coding this up, you don't want to just code, you might code it up and say, okay, I'm just going to do 10 iterations every time, and I don't care, if that wastes computer time. But you don't really need to, if you're checking the error in your iterations, sometimes you could save time by just doing 1 iteration. And then 0.95 gets even worse, can be 8 iterations. Again, where there's a lot of curvature in that function, it's going to take a lot longer to iterate. And then we go to 0.99, and then it really starts to fall apart because it can just wander all over the place. It could take 800 iterations. Or depending on what kind of computer on, it may not converge at all. So when you're at an eccentricity of 0.99, it gets so nonlinear that it could be that it's not going to converge just because of the accuracy of the digits on your computer, depending on what your computer you're working on. So I don't recommend this for really extremely high eccentricities. So, of course, there's an algorithm in Velato to do this, which you've already had some experience with, so I'm going to skip past that and go on and talk a little bit more about the orbit elements. So it's kind of picking up where Mark left off last time. He kind of introduced these. The slides that I gave him had a number of different plots that showed orbit elements. I really like Velato's plot from your book. But there was one from another classic textbook in the notes for lecture 5. But it's really important to be able to visualize these orbit elements, to get a visual feel for how the orbit is oriented. Remember that what we've done so far is, we've got our orbit plane, and we determined for a 2-body orbit that the orbit plane contains the position and velocity vectors of the satellite, and we could have 3 orbit elements that tell us the size of the ellipse in the plane, that's the same major axis, how eccentric it is, the shape of the ellipse, that's the eccentricity, and then the true anomaly is the angle that tells you where you are relative to periaps. So, but remember I also said, and this is now the week before last, but we know, so the orbits contained in this plane of this paper, we know how to determine the position of the satellite in that plane. We also know by our solution to the two-body problem and Kepler's equation, all that, how to propagate the orbit in time. We know how to relate its position to time through Kepler's equation. But we don't yet know how this plane is oriented in space. So now for the two-body problem, the plane ends up being fixed in space. Like I've said before, it's fixed in inertial space. So with respect to the stars, it's fixed. And so what we really need is a way to basically tell us how it's oriented with respect to the stars. And I think it's pretty straightforward to understand that that 3 independent angles would tell us how that plane is oriented with respect to the stars. And the 3 that have, those are not unique angles. I mean, I can give you the 3 that we're going to use, but then you could come up with another 3 that are completely different. So these are kind of by definition, people developed these angles, and they've kind of become accepted, over time as the angles to use to define the orbit. So the angles are, well, first let's start off with the line of nodes, and this is a little review, but it never hurts to review a little bit. Line of nodes is the intersection between the orbit plane and the equatorial plane. So the line of nodes is pointing out here, and the angle between the line of nodes and the x-axis of the inertial system. So Vlado uses capital I for the x-axis of the inertial system. Now later, I think maybe on Thursday, we'll talk about exactly how that x-axis is pointed. But for right now, just assume there's that we define this inertial frame with respect to the stars. So that x-axis, just think about pointing out at some fixed star somewhere. So, and we want to orient our plane with respect to the stars. So if we can orient our plane with respect to the x, y, and z axis of our inertial system, which is fixed to the stars, then we'll know how our orbit plane is oriented with respect to the stars. So the first one we use is the right ascension of the ascending node, capital omega. So that's the angle between the line of nodes and the x-axis. The other one is the argument of periaps. And so the argument of periaps is the angle between periaps, and we define the periaps direction is defined by the eccentricity vector. So that's a vector. You can compute that vector pretty easily, and it tells you in this inertial frame where periaps is. So that's really useful. It also turns out if you take the magnitude of that vector, you get the actual eccentricity of the orbit. But in this case, it's telling you where periaps is relative to this inertial frame. So the angle between the line of nodes and that periaps vector, or eccentricity vector, I'm sorry, the line of nodes and the eccentricity vector is little omega, the argument of periaps. Then the other angle we need is this one up here, the inclination. So that's the angle between the angular momentum vector and the z-axis. So those 3 angles uniquely define how this orbit plane is oriented in space, and that's all review because Mark talked about that last time. He also used the law of cosines to show you how to compute these different angles. So you have everything you need to kind of compute a set of orbit elements for the satellite. Like I said, these angles aren't unique. You could produce another set of angles that would also tell you how the plane's oriented in space, but they'd be defined in a different way. Any questions about this? Okay, so now the other thing we're going to talk about today is it's going to become necessary to be able to take a vector expressed in the plane of the orbit, and I'll show you that in a second, and re-express it in terms of the inertial frame, ijk shown here. So, and to do that, and I'm previewing a little bit here from a few slides from now, but we're going to use something called principal axis rotations. But I wanted to show it on this slide a little bit just because, you know, it is possible, and this has probably come up in I'm sure other classes you've had over your college careers, but if you have one Cartesian system, and then there's a different Cartesian system that has the same origin but different axes directions from the first one, it's actually possible to take a vector represented in one and rotate it and get the same vector expressed in the other Cartesian system. And so that's kind of the concept we're going to use to take a vector that's expressed in terms of the orbit plane and get it into the inertial system. I'll introduce that here in just a second. So we now understand what orbit elements are. So where do we get orbit elements? And I believe Mark showed this last time as well. There's a new homework 3 out there as of this morning, and we're going to be writing some MATLAB code to do some of these calculations and then testing it. And I give you a link to where you can get these 2-line element sets as well as to a descriptor that talks about what the definitions are. But from these 2-line element sets, which is really just a big text file, it's the same text file though that Heavens Above website reads in to do, say, the ISS predictions. So we can go through here. You can look at the definition of the terms up here. Some of them you recognize, some of them you won't. I've rewritten them down here. But you get the mean motion. From the mean motion, you can compute the semi-major axis. They give you eccentricity, inclination, rate ascension, the ascending node, argument of periaps, mean anomaly. These extra terms, they also give you the time. These other terms down here are related to basically to drag. And so we haven't really introduced the concept of drag yet, so we'll get to that later. But these are, imagine, so mean motion is the angular rate at which the satellite goes around the orbit. And so just conceptually, you can see how a drag force is going to be acting in the negative velocity direction. Is going to retard your mean motion. And so these terms here, n dot and n double dot, would represent how much drag your satellite's experiencing as determined by NORAD, who produces these elements. So, but right now for our two-body orbit, we don't have any drag, so mean motion is constant, and we just get that. So, and then there was this little example here, which I also have, in the homework it talks about testing your code with some examples in the book. But you can pull out all, here's an example piece of the 2-line element set. So it's just 2 ASCII lines, and you pull those out, pull the terms out from them, and you can write out the orbit elements. So, and the last note down there is probably something I should mention. The errors can be as large as a kilometer or more. So these 2-line element sets are not for precision orbit calculations. They're for well, give you an example. I've used them before as an initial orbit to decide where to point a laser to actually do precise tracking of a satellite. So it's often used for acquisition by ground-based satellite tracking systems as an initial orbit, initial guess of where it is in the sky. But the errors can be large, even larger than a few kilometers. So it's important to know that if you decide to use these 2-line element sets, it's just your most basic orbit you can imagine. Also, I mentioned this when I talked about that Heavens Above site and the ISS predictions, but if the satellite maneuvers, well, these 2-line elements have no way of knowing that the satellite just fired its rockets, and so then they become invalid. So your prediction with these 2-line elements be going this way, then the orbit after the maneuver is going that way, and so you got to also pay attention to that. These, as I recall, these tend to be updated by NORAD every couple of hours, roughly, and it kind of depends on how often they get tracking data. So, but if there's a maneuver within those couple hours, then you could be off by quite a bit. So, last time Mark went through this algorithm of how to get orbit elements from position and velocity in time. And so it's algorithm 9 in the book. This is one of the algorithms you'll code up in the homework this week. So the way to attack this homework is just simply to code up the algorithm from the book. And then what's nice about Velato is whenever he gives an algorithm, he almost always gives an example using that algorithm. So then and he gives the answer. So then you can test your code and make sure you get the same answer he did. And then go, maybe I've asked you to do some problem in the homework. Then you can go use your code after you've tested it from the Velato example. So if there's any questions about this, now would be a good time to ask them. But all of these were basically derived from the law of cosines. It's not the only way to do it. And one of the disadvantages of doing that this way is that when you use the law of cosines, you're going to end up doing an inverse cosine, and it gets back to the same quadrant problem I mentioned earlier, where there's actually two possible angles that will come out of these. You need to know which one to choose. And so these rules over here will allow you to determine whether you need to adjust the phase of the angle to a different quadrant. But it is pretty foolproof, and the law of cosines is pretty easy to understand to relate the angle between two vectors. So that's kind of your recipe for determining orbital elements from position and velocity. And then also these equations here. Then you code all that up, and then you have an example in the book. So here's the example for that the Velato has. So again, you're starting with a position and velocity, and these are in the inertial frame. So again, Velato's using IJK for the inertial frame. So now you want to find all the classical orbit elements. So you start by computing your angular momentum vector, which is the cross product of position and velocity. And you also want the magnitude of that, so he computes the magnitude of the angular momentum vector there. Then he finds some other parameters that you need, like, for instance, the node vector. The node vector you need because it shows up in the definition of the right ascension of the ascending node and also in the argument of periaps. So the node vector is just the cross product between the z-axis of the inertial frame and the angular momentum vector. So k here is just 0, 0, 1. And then the angular momentum vector is from the last slide. So you do that cross product, and you get that. Eccentricity vector. I assume that Mark gave you this equation, but if he didn't, I usually don't derive this. I just kind of give it to you as right here. So you have the eccentricity vector. You can compute it from, what do we got here? Just position and velocity is all you need. And so you get this eccentricity vector. And again, that tells you if you're at the origin of the inertial frame, which is at the center of the Earth, it tells you basically what star that periaps is located at, what direction that is. So you could also take the magnitude of that and get your eccentricity. In this example was 0.083. And then you compute the energy, b squared over 2 minus mu over r. So the orbit's not parabolic, so we can find the semi-major axis through this version of the energy equation here. So this is 36,127 kilometers. They go on to compute the semi-parameter, which is this h squared over mu. And then they start by determining the angles from that law of cosines. So the first one is the inverse law of cosines. Remember that the inclination is just the angle between the z-axis of the reference frame and the angular momentum vector. So that also, of course, the inclination is also the angle that the orbit plane makes with the equator. So, and it's all, the inclination's often useful because it tells you how much of the Earth you're going to see in terms of latitude and longitude. If the inclination is 20 degrees, then you're going to see plus or minus 20 degrees latitude and longitude. But at the same time, when you start tilting the orbit with respect to the equator, that tilts the orbit plane with respect to the z-axis or the pole. And so that's why we can compute this angle. There is no ambiguity here for the quadrant, so you don't have to do a quadrant check. It's just 87.87 degrees. Then you compute the right ascension of the ascending node. And initially, the value you get out of this is 132 degrees. But then you check the jth component of the node vector, and you find actually it is negative. So then you take, get the final value for the right ascension of the ascending node, you take 360 degrees minus that 132, and that gives you the final value. So just a little if statement you put into your MATLAB code. And then similarly for the argument of periaps, again, the angle between the node vector and the eccentricity vector. The true anomaly is the vector between the eccentricity vector and the position vector. And so you get these angles out. Now also remember that Mark talked about some of these auxiliary angles. The auxiliary angles only come up when you have special situations. So, you know, for instance, the angles that you introduced last time were the true argument of periaps, the argument of latitude, and the true longitude. And if you want, you can compute these in your code. I don't normally deal with cases like this, but if you do a lot of astronomical calculations where either the inclination is close to 0 or the eccentricity is close to 0, then some of these auxiliary angles are helpful. So, because remember, as an example, when the eccentricity is almost 0, then the argument of periaps becomes undefined. And so how you're supposed to figure out what direction periaps is if there is no periaps. If there's no closest approach to the Earth, you won't be able to compute it. And so so instead, you compute this omega tilde true as an alternative to the argument of periaps. So, and if you are kind of an amateur astronomer, you may have seen angles like this before. And so, because a lot of astronomers will use these alternative definitions to the classical set that I use. So this was just defining what that longitude of periapsis was. Going to skip that and go back to our orbit elements. So here's where I want to start talking about the principal axis rotations and how we use them. So we now have an algorithm where we can, given a position and velocity in the initial frame, we can compute a set of orbit elements. And like I said before, the advantage of doing this is that for a satellite that's moving in orbit, all 6 components of position and velocity are constantly changing. But now when we express it in terms of orbit elements, at least for two-body dynamics, only the true anomaly is changing. So that's the main reason that we do this transformation from position and velocity to orbit elements. Now the other reason is that orbit elements are a lot easier to visualize. So if you were to look, you were in a meeting somewhere and someone was to put down the table a position and velocity, the vector position and velocity, I would challenge you to actually know anything about that satellite orbit from just looking at those. I mean, you might quickly look at it and say, oh, it looks pretty far away from the Earth. It's a high orbit. Or, oh, that's pretty high velocity. I wonder if that's got escape velocity or not. But you really wouldn't know much about the orbit. Instead, you go and compute someone was to put down the 6 orbit elements in front of you in a meeting, you would immediately know basically the altitude of the satellite from the semi-major axis. You would know the shape of the orbit from the eccentricity. From the inclination, you would know kind of what latitudes it sees. And we'll look at some of these properties later. And the whole variety of things that inform you about what the satellite's going to do. But there's also going to be a case where you might have a set of 6 orbit elements, and you want to compute a position of velocity in the inertial frame. So we got to be able to go back. We just learned how to go from position velocity to orbit elements. Now we need to do the reverse. And so, and there's a lot of reasons you might want to do that because there's still a lot of useful applications for the Cartesian position and velocity. There's a lot of calculations I'm going to show you that are best done with Cartesian vectors. So, for instance, I'll show you later how to compute the latitude and longitude of the satellite. That is best done in Cartesian frames, not with orbit elements. So, and yet it's easiest to propagate the orbit with the orbit elements because only the true anomaly changes. So you're going to be going back and forth a lot. The homework this week is actually just developing the code for both of those instances. Position velocity, orbit elements back to position velocity. So let's talk in detail about how we're going to go from orbit elements back to position and velocity. So the way it works out best is that we can use our orbit elements to compute where we are in the plane of the orbit here. And let me use the whiteboard over here. I got some figures for this later. But if I was to draw out the orbit on the board, and let's say this is periaps here, what if I set up like a coordinate frame? And the position of the satellite is here. And this is the true anomaly. So the coordinate frame has the x-axis pointed this way. And in Velato, they call it x-axis. They call that P for periaps. And then they call the y-axis is 90 degrees to that, so it's perpendicular to that. So the y-axis they call Q. And then to complete the frame, there's obviously a Z coming out of the board. They call that W. Yes? No, the origin's at the center of the Earth. Yeah, so there's another empty focus over here. Sorry, I draw things poorly, which is why I often use slides. So it turns out that we can very easily express the position and velocity in this PQW frame. So we can write down, and I'll show you this in a second, we can write down R in the PQW frame and V in the PQW frame. There's equations for those I'm going to give you in a minute. And those equations are actually in terms of the orbit elements. Remember, we're starting with orbit elements. We're trying to go to, what we're trying to get to is we want to be able to write down a position in the IJK frame and a velocity in the IJK frame. So the procedure we're going to use is we're going to use our orbit elements. We're going to express the position of velocity in this PQW frame, which is in the plane of the orbit. And then we're going to use this idea I mentioned earlier, principal axis rotations, to rotate this vector here, and through a series of 3 rotations, rotate it into this frame here. So, and we do that using this idea of principal axis rotations, but I'll show you the equations for that. But remember, right now we've got our x-axis pointed out at periaps. That's the p direction there, and then our y-axis points perpendicular at Q, and then the z-axis W points out of the board. And so we want to come up with a set of rotations that's going to sequentially perform 3 rotations and get it so that our x-axis is pointed towards I here, our y-axis is pointed towards J, and our z-axis is pointed towards K. So let's look at how we do that. And but a lot of this is, I think you're going to have to go home and think about this a little bit outside of class and try to work out these rotations in your head, try to visualize it. The math is easy, and I start always with just a little example of not the orbit problem, but just a standard problem where we have a vector expressed in this xy frame, and we want to express that same vector, but in components of the x prime y prime frame. And the relationship between the xy frame and the x prime y prime frame is just this angle theta. So it's just offset by an angle theta. We're just doing this in 2 dimensions. I'll explain that in a second. So yeah, we can and draw this out. So in this vector is right here. That's the end of the vector, r, x, y, z. And so its x component is here, y component is here. And so now we want to re-express it in the primed frame. So now we want to compute our x prime and our y prime given our x and our y. Well, because we know the 2 frames are just related by this angle theta, in essence, the prime frame is rotated by an angle theta with respect to the x frame. If you use the right-hand rule And we're going to rotate about the axis coming out of the board, which is the z-axis. Obviously, the z-axis for these two frames is the same. Whatever axis you rotate around, the components of that axis don't change. So, the the RZ component here is going to be the same for the prime system as well as for the original system. So you rotate, right-hand rule, positive rotation this way, right angle theta, and that will take you from y to y prime. We can derive those rotations by simply, you can look at the geometry here, and you can actually figure out what our x prime and our y prime are in terms of rx, ry, and the cosine and sines of theta. So you can sit down and study this and figure it out just by, if you put in some values of theta, you know. It's like if you put in theta equals 0, you know the two vectors should be equal. So there's no rotation. So you put in theta 0, you get rx prime equal to rx, ry prime equal to ry. So, and then you can put in different values of theta and convince yourself these equations are correct. Of course, the z terms don't change in this rotation, so rz prime is equal to rz. So you can actually take this and express it in matrix form. So matrix form, the vector in the prime system is equal to this rotation matrix, which has theta in it, times the vector in the on-prime system. And we're doing a rotation about z, and so because we're going to do other rotations about other axes, we're going to call this, we're going to call the axes 1, 2, and 3 for x, y, and z. So this is a rotation about z. We're going to call that matrix rot 3. So this whole matrix here is a rotation matrix we're going to call rot 3. Its argument is theta, whatever the rotation is, and you multiply that times the vector in the original Cartesian frame. So for this simple system, remember this system, you have an unprimed xy frame, and you already know what the vector components are in that frame. So you know rx, you know ry. You want to know if that system was rotated and you got the prime system here, how would that same vector be represented in the prime system? So you're solving for our x prime and our y prime, and studying the geometry there, you can write down these equations, relating the two, express it in matrix form, and then you get this rotation matrix. That's a, even though this is a specific example, this is the general rotation matrix for doing a rotation about z. And likewise, I just wrote them down here, but this rot 2 here is the general rotation matrix for a rotation about y, and this is the general rotation matrix for a rotation about x. So now, hopefully I convinced you that this is how you can do rotations between two different Cartesian frames that have the same origin. And so now I want to try to apply that to the orbit problem. And we're doing this because we're trying to compute position and velocity from orbit elements. So what do? Well, we start by defining that PQW frame that I wrote on the board there. So here's the PQW frame that has the angle there is the true anomaly. This is the position vector. We can write down the components of the position vector in this PQW frame like this. And it's pretty obvious. It's just our cosine of the true anomaly for the x component and our sine of the true anomaly for the y component. But we also know we have an equation for r from the trajectory equation. So if you substitute that in, you can get for the vector in the PQW frame, you get p cosine nu divided by 1 plus e cosine nu, p sine nu divided by 1 plus e cosine nu, and then 0. There's no, in this PQW frame, there is no z component because the satellite's in the plane of the orbit. And so there's only x and y components for the satellite position in the PQW frame. So now writing down the velocity in this frame is a little more difficult. The approach that's taken here is to just take the derivative of this rpqw to get the velocity in the perifocal frame, and then using some of the relationships we developed in our study of the two-body problem. We have relationships for r theta dot or r nu dot is equal to h over r, and we can also derive a relationship for r dot from taking the derivative of that. I'm not going to spend time on the details here, but suffice to say, you can work all this out and get down to a velocity in this perifocal frame can be represented like this in terms of orbit elements. And again, the velocity is contained in the orbit plane, so there is no z component to the velocity. So now we have, I just gave you equations for r PQW and v PQW. So we have vectors for those now. So now if we can just rotate these into the inertial frame, then we'll have the answer that we wanted, which was to get the position and velocity from the orbit elements. So here's the part where you have to go home and think about this, and then please come see me if you, after you've thought about it, you can't really work it out in your head. I'm going to describe how these are done, but you really need to think about it in your head. I've yet to come up with a really good visual aid for this. If anybody has one, I would love to throw it into the lecture and talk about it next time. But I'm going to try and do this by starting from the equations and see if we can visualize these rotations. So again, this is the three rotations that you do to go from the position of velocity in the perifocal frame to position of velocity in the inertial frame. And it's the same set of rotations you put on the velocity vector. So we just talked about the position vector for now, and it's the same rotations for the velocity vector. So you start with your vector in the PQW frame, which was that previous slide. So this is your vector in the PQW frame. So the first rotation you're going to do is a rotation about z by minus omega. So remember, a rotation about z doesn't change z at all. Right now, our z is still pointed out perpendicular to the orbit plane, so it's pointed out in the direction of the angular momentum vector. We're going to do a rotation about z by minus argument of periaps. So that's, remember, right now, our x-axis is pointed in that p direction, so our x-axis is pointed out in the direction of periaps. But remember, the argument of periaps is the angle between the direction of periaps and the node vector. So by doing a rotation by minus omega, we're going to rotate our x-axis from pointing out at periaps to now pointing out along the node vector. And so after you do this rotation, you end up in some intermediate frame here. And so that's just part of the first step. So the first rotation rotates your x-axis from pointing out along periaps to pointing out along the node vector. The next rotation, see, it's about the x-axis. It's rot 1. It's by minus I. And so, again, if you're looking down the node vector on the side of the orbit, what we're doing is we're rotating about x, and so that's going to by minus the inclination. So now we're rotating our z-axis. Our z-axis was pointed out along the angular momentum vector when we started. Now it's going to be rotated, so it's pointing basically towards the z-axis of the initial frame, so essentially the Earth's north pole. So we just did a second rotation by the minus the inclination, so it's negative. So if you remember, all these positive rotations are the right-hand rule, so when you do a negative rotation, it's the opposite direction. And so it's taking our, this particular rotation, let me draw a little help here. If we're looking down the node vector, we're looking at the edge of the orbit. And the angular momentum vector is pointed in this direction. The z-axis k is pointed in this direction. And the inclination is here. So if we're doing a negative rotation, we're going to take our z-axis that's here, and we're going to rotate it until it's lined up with the k-axis of the inertial frame. So that's what this second rotation does. And then the last rotation is rotating by the right ascension of the ascending node. And it's a rotation about z again. So, because we already got z where we need it. Z is pointed along the k vector, which is what we want. But now, so we need to think about what does that angle tell us. If we go back here, here's the right ascension of ascending nodes. We're doing a rotation about z. And so we're looking down on this, and we're going to rotate the x-axis from the line of nodes over to here, because we're doing negative the right ascension of ascending nodes. So that last rotation, it's going to take the x-axis here and rotate it so it's pointing along the I direction. And so then we're done. So So that's the last rotation. That gives us, now we've got all the vectors all rotated and expressed in the IJK frame, the initial frame. So we have the position of velocity in the initial frame. You do exactly the same rotations for the velocity vector, and you're done. So this is really a transformation that's taking from the PQW frame to the IJK frame, which is why it's written that way. Now, you're going to be coding this up in the homework 3 from that algorithm in the book. Now here, what I've done is actually multiply together these 3 rotation matrices to get this one big 3x3 rotation matrix. So you can combine all the rotations. I'm not sure I would recommend that because it's too easy to make an error in a sign or something here that might be hard to find. I would just tend to code it up exactly like here. So define these rotation matrices 1, 2, and 3. That's where MATLAB is really good, right? Because you can define them all as matrices and multiply them together easily. And then just in your code, have exactly these lines of code, just doing those rotations and rotating your vectors in the PKW frame. I think that is, that's one other comment. The order of the rotations does matter. So you can't start flipping these around. It's just like Euler angles. For those of you that have worked with Euler angles before, if you were to change the order of the rotations, then they wouldn't mean the same thing, and you wouldn't get to the same result. So now what I would suggest is going home and using whatever tools you want to use to try to visualize how these rotations take you from the PQW frame to the inertial frame. But I think it's, if you can't figure it out and you want to talk to me, come see me in office hours on Thursday or any other time you find my door open. So then you're going to code this up in MATLAB. You're then going to use the example in the book. Here's the example where you're given a set of orbit elements and you're supposed to find the position and velocity in the inertial frame. And so just very quickly, you'll do this to just test your code. But you start out by writing the position in the PQW frame, the velocity in the PQW frame from these equations. So you actually get vectors out of that. And those are what you're going to apply the 3 rotations to. So and it's really just a couple lines of code. So the MATLAB anyways. So that's gives you the position in the inertial frame, velocity inertial frame. Those are if you multiply these 3 rotation matrices together and compute the components, this is the 3x3 matrix you get of the combined 3 rotations. Like I said, I'm not recommending you combine all the rotations, but if you want to, you could check your code by printing out that matrix. So when you apply that matrix so that matrix is going to multiply the PQW vectors here, and when you do that, those are the results you get. Okay, so just one more concept I'd like to cover in the last 10 minutes, which is this concept of F and G series. It's again related to the two-body problem, so I kind of want to finish up this, if I can, get the two-body problem completed today. So the data here is that we just learned that essentially we can express the position and velocity in that PQW frame, and we can also express. Turns out that what F and G series is going to tell us is that we can express the position and velocity as a function of some initial position and velocity, R0, V0, through these F and G functions. So that's basically the idea of this F and G series, is that there's a way to express the position and velocity as a function of some initial position of velocity. So you think this is not possible given what we know about the two-body problem already. Turns out you still have to use Keplers Equation and mean anomaly and things like that. It's not really a way around that. It's more of a mathematical way of representing things. So what we want to do now is we want to solve for the F dot and G dot that will allow us to relate the position and velocity at some future time to the position and velocity at some earlier time, R0 and V0. So we start with these equations. And there's a derivation here in the notes where you can derive the expressions in terms of the F and G series. So we start by crossing the position vector into the initial velocity vector. Remember, the position vector is F R0 times plus G V0. You cross them together. This term is 0 because a vector crossing into itself is 0. You get R0 cross V0, which is H, which is constant. And so you can relate this cross product up here can be expressed as just F times H. That allows you to solve for the F function. So we have our first function that we need. You can differentiate this and get the F dot that goes into that previous equation. Again, so those two, the F and the F dot, are what you would put in here, F and F dot. We're trying to solve for those two, and then G and G dot. Then we'll have a way to relate future positions and velocities to a past position and velocity. So then you do the same thing for G by crossing R0 into R, the position vector. So R0 is just your initial position. R is your position expressed in the F and G series. And again, the vector crossed into itself is 0. So this turns into G times R cross V, which is H. So you get GH. This is the result of taking that cross product there. So you can solve for G, take the derivative, get G dot. So now we have expressions for F, G, F dot, and G dot. And then in the derivation in the book, he also uses this expression to get this constraint on the whole system. So he looks at the angular momentum vector in terms of the F and G series, and he can show that that the F and G that will satisfy these equations are the ones that make this expression true. And he derives this expression by looking at the angular momentum in terms of the F and G functions. So 1 is equal to F times G dot minus F dot times G. So now we have a way to compute all these F and G functions. So we start by computing our x, basically our position and velocity in that PQW frame. And so that's the same equations we used in the orbit element discussion just a minute ago. Once you have those x and y functions, you can compute your f, g, f dot, and g dot. The only problem there is that if you go through the derivation, you end up finding there's this delta true anomaly that is in there. And that delta nu that's essentially the angle between R0 and R. So it's essentially how much has the true anomaly changed between the initial position and velocity and the final position and velocity. So and so we're still going to be faced with, okay, we don't know how delta nu changes as a function of time, so we're still going to have to use Kepler's equation and those kind of things to deal with this. It doesn't turn out to be a way around of using all the anomalies in Kepler's equation. But it's still, the reason it's presented in the book is that this is a succinct way of mathematically showing how to relate a position and velocity at some time t0 to a position and velocity at some future time. So that just kind of summarizes that relationship. I did it very quickly. I apologize, but you have your R0 and V0 here, and you can relate that to a future position and velocity through these f and g functions. They're computed over here, and you can look at that in the example 2.4 in the textbook to test that. But you also need that change in the true anomaly, and so that's the angle between your two position vectors. And so you're still going to have to solve for that to do this propagation from the time t0 to some initial time. But it is useful as a mathematical tool for representing the position velocity at one time to the position velocity at another time. And that's shown here where they essentially use these f and g functions to compute what's called a state transition matrix. If you take advanced classes here in kind of orbital dynamics, you'll learn about how it's common to represent the dynamics of a satellite in terms of a state transition matrix. And that allows, the state transition matrix allows you to relate one state to another state. The state is just the position and velocity all in one vector. So it's 6 components, of 3 components of position, 3 components of velocity. And you can relate the state at one time to the state at another time via the state transition matrix. That transition matrix just has, if you break it up into the 4 blocks, each block is just a diagonal matrix that has the f functions on the diagonal for f, or f dot on the diagonal, or g on the diagonal. So, we may not really get in much in the state transition matrix much more in this class, but if you take like an overdetermination class, it's a common way of succinctly representing the dynamics in an equation like this. So last thing, and then we'll let you go. So what are these f and g series? What uses do these functions have? So a couple of different things. One is, given 2 states, so given 2 positions of velocities, you could use this to find the time of flight between them. Also, given 2 states, you could also use this to find an orbit that connects them. And in fact, that's kind of a general, that's related to something called Lambert's problem that we're going to look at later. Given two states at 2 different times, what's the orbit that goes between them? You can imagine a lot of applications for something like that. So we'll talk about that much more later. And then using an iterative technique like the Newton-Raphson, you can determine a future state given the current state and a transfer time or transfer angle delta nu. So that's just that's something F and G series. It shows up on almost all the major astrodynamics books and also in Velato. So I wanted to make sure we at least briefly covered it. So next time we're going to get into this preview slide here. The next lecture is going to start talking about coordinate time systems. So we're done with the 2-body problem for now. Well, the 2-body problem will keep on coming up and coming up throughout the rest of the semester. So word of warning, if you feel like I may have lost you somewhere along the way, just speak up and come and talk to me and ask questions in office hours or elsewhere. And I'll try to clarify things because I want to make sure that we all got this fundamental down so we are ready for what comes next. So I'll see you guys on Thursday.